Welcome back. In this problem, number 2a, we're going to be looking at the exact same series as in problem 1, which we were able to compute with a geometric series test. But this time, we want to show that it converges using the absolute convergence test and the integral test. So the absolute convergence test is simply going to say, if I replace the underlying sequence with the absolute value of that sequence, which essentially here is just going to get rid of this negative. And if the series that I get converges, then the original series converges, right? So I can just pretend there was never any negative, and if I get a convergent series, then my original series converges. So let's start with that. So and remember we abbreviate absolute convergence test with ACT, by the act, if the series from 2 to infinity of 3 to the n over 4 to the n plus 1 converges. Okay, notice the absolute values are unnecessary with any of the other pieces because they're all positive. Then the original series, so that has a negative 3 to the n over 4 to the n plus 1 converges. Okay, so I replace a series that's complicated with one a little less complicated. Now I want to use the integral test. So for the integral test, I need to find a generating function for the sequence terms. So this is pretty easy in this situation. I just replace my n's with x's. So I would get 3 to the x over 4 to the x plus 1. Now if I want to do some integration, it might be a little better to rewrite this. So first, I can write the 4 to the x plus 1 as 4 to the x times 4 to the 1. And so I could write this now as 1/4 times, since the x is on both exponents here, I have 3/4 to the x. All right, so what does the integral test tell us? Well, if we can show that this generating function is continuous, eventually positive, and eventually decreasing, then instead of checking whether or not this series converges, I can instead check whether a corresponding integral, an improper integral, converges. All right, well, let's write down these hypotheses, right? So we need f, all right, needs to be continuous. Well, where does it need to be continuous? Well, from 2 to infinity, right? So continuous on 2 to infinity, which is not going to be an issue here. This is an exponential function. Exponential functions are continuous. Multiply by a fourth, it's still continuous, so that's no problem. It also needs to eventually be, well, I said positive, non-negative is good enough, so it needs to be non-negative. Well, that's not a problem either. You're taking an exponential function. That's a positive function, in fact, right? We could have said positive. So that's also true. Let's see. It needs to be a decreasing function. All right, so this needs to be decreasing, or at least eventually decreasing. In this case, it will always be on 2 to infinity. Is that going to be the case here? Yeah, actually it is. So one way that you can, I mean, there's sort of a general rule here, right? When you have an exponential function and the base is less than 1, then that will be a decreasing, right, or a decaying exponential function. The other way you might think about it is 3/4 to the x is the same as 4/3, so I've inverted 3/4 to the negative x. And now you can see this as being, okay, 4/3 is greater than 1. And so if you wanted to plot this, right, 4/3 to the x, that might be 4/3 to the x. But when you raise it to a minus x, right, this is going to do a horizontal reflection. So this would be our 4/3 to the minus x. So this is actually a decaying function. So it's decreasing. Okay, so we have a decreasing generating function as well. So we're allowed to use the integral test. And now the integral test is going to say that if, so by the integral test, if the integral from 2 to infinity of our generating function converges, then the series that we wanted to compute. So this was the 3 to the n over 4 to the n plus 1 converges. Okay, so let's back up a second. We started with this series. I had a negative 3 to the n over 4 to the n plus 1. We used the absolute convergence test to get rid of the negative. And now we use the integral test to turn this from a series convergence problem into an improper integral convergence problem. Okay, well, let's see. The integral from 2 to infinity of f. Well, what was f? F was a fourth, which I can pull out, 3/4 to the x. All right, so you got to remember your exponent laws for anti-differentiation. And you say, okay, let's see. Well, okay, it's an improper integral, so we can say a limit as, say, some b goes to infinity. And then what are we going to have? Our antiderivative is 3/4 to the x divided by ln of 3/4. And then we need to evaluate this between 2 and b. All right, so let's see here. When we evaluate this at b, now this is just a constant on the bottom, right? That I could pull all the way out as well. So I'm really just looking at what happens as b goes to infinity with 3/4 to the x. All right, or 3/4 to the b when I evaluate it. And of course, we saw what happened. Go up to our picture. All right, as your input gets bigger, right? This is a decaying exponential, so this piece will go to 0 as b goes to infinity. So we have our 1/4. When we evaluate at b and let b go to infinity, we get nothing. And I don't really care too much what happens when I evaluate it at 2. I can work it out, right? We'll get 3/4 squared over ln of 3/4. But it's just a number, right? That's the key. You just get a number. And sorry about that, little one-note issue there. So we just get a number, which that's all that matters, right? Because it says that this improper integral converges, right? So this implies that our improper integral converges. But now going back up, that says that this intermediate series converged. But that intermediate series, by the absolute convergence test, that implies now that the original series, well, we can do a better infinity. There we go. The original series, negative 3 to the n over 4 to the n plus 1, that series converges. Okay, there we go. Absolute convergence test and integral test.